Good afternoon, and welcome to the Water Research Foundation and Water Environment Federation co-sponsored webcast on Reform EBPR Design for Sustainable Nutrient Removal with Carbon and Energy Recovery. My name is Stephanie Fiebig. I'm a research manager with the Water Research Foundation, and I will be your moderator for today's webcast. The discussion today will focus on a new Sidestream enhanced biological phosphorus removal process, also referred to as S2EBPR, that involves a Sidestream anaerobic biological sludge hydrolysis and fermentation reactor to address the common challenge in EBPR related to weak wastewater influent and also to improve EBPR process stability. This work was recently completed under Project U1R13, Optimization and Design of Sidestream EBPR Process as a sustainable approach for achieving stable and efficient phosphorus removal. Under this project, the research team examined the fundamental mechanisms involved in the S2EBPR process and developed criteria for effective design and operation. The project report is now complete and it's available on our website through the link provided. A follow-up project, number 4975, is actually going to kick off next month, and that project will be led by Dr. Leon Downing with Black & Veatch alongside Dr. Gu and Dr. Bernard. Before we get started, I want to cover a couple housekeeping items. First, we will have a Q&A at the end of the webcast. I will show you how to submit questions in just a moment. Also, the presentation slides and recording will be available within 24 hours after the webcast. If you would like training unit credits, please send an email to Michelle Suazo and she can send you a certificate. Also, we have a survey at the end of the webcast. There will be 3 post-event questions that will pop up. Please be sure to answer those questions so we can hear your input. This slide shows you how to submit your questions during the webcast. You can do so by typing your question in the box to the left of your screen. If we do not get to your questions today, we will respond to you via email. Also, the slides will be available for download. Just under the question box, you'll see an Event Resources tab. Here's where you can download the slides. Now I'd like to introduce our speakers for today. Our first speaker is Dr. April Gu. She is currently full professor and Atkins Center for Sustainable Future Facility faculty fellow in the School of Civil and Environmental Engineering at Cornell University in Ithaca, New York. She has a BS in Environmental Engineering and Science from Tsinghua University in Beijing, China, and a PhD in Civil and Environmental Engineering, jointly in microbiology, from the University of Washington. Dr. Gu was a process engineer for over 7 years prior to her academic career and has a variety of experiences in wastewater treatment planning and design, pilot testing, and design of cutting-edge technologies and innovative process solutions. Dr. Gu is an elected Fellow of WEF for her professional achievement and contributions to the water profession. She is among the recognized world leaders in EBPR technology, and she has served on national and international professional organizational committees. Another well-known name in the BNR world is Dr. James Bernard. He developed the Bardenfo MLE and 4-DOX, also known as AO or A2O processes, for biological nitrogen and phosphorus removal, and he has designed more than 140 BNR plants worldwide. He served on advisory committees for New York, DC Water, Los Angeles, Winnipeg, and others. He was awarded the Clark Prize in 2007, received honorary doctorates from the universities of Johannesburg, Iowa State, and Stellenbosch, and the Lee Kuan Yew Singapore Water Prize in July 2011. His research into biological phosphorus removal has unveiled some new perspectives which are disrupting existing notions. He is presently employed by Black & Veatch in Kansas City, Missouri as a global practice and technology leader. And with that, I'd like to hand it over to Dr. Gu.
Thank you, Stephanie. So we'll start today's presentation with a little bit of history of Sidestream EBPR by James, and then I'll give a summary of the findings from our work study. And after that, James will also give you more recent current practice updates on the implementation of Sidestream EBPR. Then at the end, we'll summarize with some take-home messages, as well as a brief introduction of current ongoing work and the future direction. James, please. Hello? Hello? Hello?
Sorry, I forgot to unmute. Too much pressure here.
Oh.
I'll start all over again. The first slide here is early attempts at biological phosphorus removal. Biological phosphorus removal was observed in a number of plants, but nobody could really explain why it happened. And this first process, the PHOSA process, was developed with a notion that if we strip the phosphorus out by making it anaerobic in what is shown here as a stripper, then the bacteria will be so hungry and that they will get back in the aeration basin and just take up all the phosphorus that's in the influent. This process worked as a high rate process, non-nitrifying. The minute nitrification kicked in, the process failed. But with the stripping process, the phosphorus that was in the supernatant was then treated with lime. Later on, as we understood more, this process was first installed in Truckee Meadows in Nevada, and it was then converted by Narayanan, as you can see on the right-hand side. On the next slide, the other observation that was in a plant, as I said, that didn't nitrify, but the other observation was in this four-stage process that I developed in the lab and then tried out on a 100 meter cube per day pilot plant. This was in 1972. And to fit in the four stages in the existing basin that you see on the right-hand side, I had to partition off what I thought was a dead zone. And it turned out that it wasn't a dead zone, but it took me 10 years to find that out. And in between these two zones, the anoxic zone, which you see over there, and over on the where the mixer is, and the fermenter zone where the arrow is pointing, there were two holes, two 1-inch holes, and I couldn't imagine that with those two holes there could have been that exchange of mixed liquor. But apparently mixed liquor passed through the holes and it fermented in this basin here and then passed back into the anoxic zone. When I took a profile through the plant, the phosphorus coming in was 10, and you can see the numbers there, 8, 7, and in the second anoxic zone there was a release of over 30 milligram per liter, and this uptake to very low values. They didn't measure below 0.2, but it was consistent every day. And I tried to do this in the lab. I didn't succeed, and so I got to the idea of putting the anaerobic zone up front, where I know I could possibly make it anaerobic by putting in the primary effluent. That wasn't totally true. It didn't work out exactly that way. It worked out in some plants, but sort of after a number of plants were already constructed, Poos and Chen came up with a theory that these PAOs need a supply of volatile fatty acids. When I designed this plant in British Columbia, it was clear to me that especially in winter there would not be enough volatile fatty acids in the influent, and the idea was then to take some primary sludge and ferment the primary sludge and take that supernatant with the volatile fatty acids and pass it on to the anaerobic zone. And since there was not enough VFA in the influent, most of the influent was passed onto the anoxic zone. That, on the right-hand side of the picture, you see other versions of that. But the problem was that, in spite of all of that, I can just add that pattern of bypassing the flow became standard in Canada, but was never copied in the US, really. And well, the result is that we passed all the primary effluent and the rest through the anaerobic zone, and especially during the rain flows, we found that the retention time was just too short. You didn't get the deeper anaerobic conditions that was necessary. That was further exacerbated by high mixing energy, which entrained oxygen. And mixing energy, I'll mention it later again, but the standard in the US was 0.75 horsepower per 1,000 cubic foot. We're down to 1/10 of that now, so that we get the mixing without entraining any air. But these conditions favored phosphate accumulating organisms, PAOs, that needed a supply of volatile fatty acids. But they also needed an anaerobic zone to make sure that only they can get a hold of that volatile fatty acids. Using Sidestream fermentation allow for deeper anaerobic conditions and volatile fatty acid production that may favor certain PAOs, such as fermenting PAOs. But the point is that we can grow a much larger diversity of PAOs. So the challenges in EBPR practice was that we have increasingly stringent permits. It demanded higher consistency and stability. Backup chemicals systems were often required, and the problem was once you start putting in chemicals, to wean the bacteria off the chemicals didn't prove that easy. So external carbon sources was required to obtain the desired carbon to phosphate ratio, and that increased the carbon footprint, and there was also a competition between the nitrogen and phosphorus demand for carbon. Alternative biological phosphorus removal strategies, we get certain benefits from the Sidestream fermentation, in that in Sidestream fermentation it's less dependent on the carbon in the influent, and so the selection mechanism is not so dependent on what is in the influent. There's a reduced dependency on RBCOD in the influent, and chemical use, and the carbon footprint lower, and potentially eliminate anaerobic zones. And this is the interesting thing, is once we put the Sidestream fermenter, we can do away with the standard anaerobic zones. And also, there's multiple flexible ways, process configurations in which this can be done, as will be explained later. And then it can enhance denitrification, as we will also see. So at this point, I just want to show you the different type of ways in which you can get Sidestream fermentation. In its simplest form is take some of the RAS, maybe today I think we have sort of settled on about 10% of the RAS, and put it in a holding basin where it can be held for under deeper anaerobic conditions for up to 2 days, and that is then fed into the anoxic aerobic basin. The rest of the RAS is just bypassed. What happens in the Sidestream reactor actually holds the key to how this whole process works. So the different configurations that were used in the study, you can see here, is the Sidestream RAS fermentation, and the process acid was applied in Canada, and especially in West Bank, where there was a Sidestream anaerobic zone. The RAS, 100% of the RAS went through, but primary sludge fermentate went in there. The total HRT was about 1 to 3 hours, but the anaerobic retention time, if we look at in the same way as we determine what the aerobic retention time is, solid retention time is, it comes to almost a 2-day retention also. The other option is Sidestream mixed liquor fermentation. We have done this at several plants now. Take some of the mixed liquor from the anaerobic zone, put it in a Sidestream fermenter, hold it there from 1 to 2 days, and then put it back in, and you can put it back in the anoxic zone. It doesn't even have to go into the anaerobic zone. And the next one is where we switch off a mixer in the anaerobic zone. And I'll give you some examples there. When you switch off a mixer, sludge settles to the bottom where it ferments. The mixed liquor just flows over the top of it. So the mixer is off for, say, 23 hours, 23 and a half hours, and only on for half an hour to refresh the sludge in here. During that time that it settles, the mixed liquor just flows over the top, and it's therefore basically a side-stream fermentation. So at this point, I'm going to hand back to Dr. Gu to tell you about the WRF project.
Thank you, James. So I will give a brief summary of the key findings in a little bit simpler without too much depth into the details what we have found through the Sidestream EBPR WRF project. So the overall goal was try to get a better understanding of the mechanism of the Sidestream EBPR process, particularly try to get enough biological understanding and insight so that we can provide the basis for future design criteria and optimization the operating conditions. So under such overall goal, we have divided into 3 sub-objectives. The first one is to using both batch scale testing as well as activity evaluation, molecular microbial ecology study, and the modeling together, try to understanding the mechanisms behind the process. And through that, in parallel, we also did a full-scale plant survey during the period of the project. We had the participation of the piloting facilities who piloted the configuration, and also control facilities who practice conventional configurations. And we did the performance as well as on-site testing to evaluate both operation parameter performance as well as ecology behind this treatment plant, try to further tease out the insights in the differences between these configurations at the full-scale setting. And at the very end, along with this, we also tried to propose and improve upon current biological process modeling for EBPR using both agent-based model as well as a full-scale model, try to see if we can incorporate some of the key understanding and to improve the current model concept and framework to reflect the performance we see with this configuration. So the summary of the full-scale facility performance evaluation, we surveyed 4 Sidestream EBPR facilities at the time, which are the only 4 at the time in the United States were able to fit the timeline to do the piloting during the study. And we also included the 5 conventional facilities for comparison. And the data was collected over a period of 3 years with statistical performance evaluation. We also did collected sample for on-site as well as in the lab scale kinetic analysis, along with microbial ecology survey and the comparison. So the treatment plant included at the time for Sidestream piloting, actually I would not say South Carey is the plant that has been running, we call it a strict, I call it a strict Sidestream EBPR SSR configuration for years. So South Carey, I consider this a true Sidestream EBPR configuration. Along with that, we also had a website regional running at SSRC configuration. Cedar Creek was piloting with the SM configuration, as well as at Henderson with inline mixing of UMF configuration. So all the 4 participating plants during that time had a relatively favorable influent BOD to TP ratio to begin with, and their average secondary effluent are shown in the table here. And note that for South Carey, they only measure effluent the total phosphorus. All the other 3 plants are reported also P. So this figure shows the concentration at the effluent to phosphorus accumulation curve as an indication of see how flat the performance was collected during the 3-year period. So from a visual perspective, the flatter the line means the system is relatively more stable. And then we can further translate that into our comparison of the percentile of the effluent concentration level. One of the potential indicator for comparison of stability is a 90th percentile over 50 percentile ratio. As you can see from the table, average of the 5 conventional EBPR plants, this ratio average out about 11 to 12. But for the 4 Sidestream EBPR plants we served during that period of time, that ratio ranges from 1.3 to 3. So it's a statistically significantly lower as indicator of more stable performance. So I try to, for those probably have already read the report, it's a rather lengthy, long report. For this presentation, I try to condense the information to really make it easier for the audience to take some clear and simple take-home message. So I organized our understanding into 3, I consider at least a current status, current understanding. So the mechanism number 1 is related to the rat fermentation and VFA production. We all know that the rat fermentation will produce VFA production, but for this project, we particularly did more testing, try to understand more quantitatively. So the particular question we had at the time was, what are the specific conditions required for rat fermentation, at least from the site evaluation as well as the lab field conditions? What are the VFA production rates and the temporal trend? And what is the VFA composition? So the key information we learned from the testing, so this is just one representative figure. So we have done many of these tests with the facilities. So in general, we see VFA production within 0 to 4, as quick as 3 to 4 hours. So at the beginning, you have VFA production accompanied by simultaneous VFA uptake by PAOs as well as GAOs and other VFA consuming organisms. So at the beginning of hours, you may have VFA production, but you don't measure the residual VFA because the simultaneous uptake. And so in this particular figure, to reflect that, we use the stoichiometry ratio between the P release as well as the VFA uptake, then back calculated how much VFA we're expecting would be consumed with it, and then added on top of the bar to reflect that. So as you can see that the residual VFA can be measured after 6 hours. I mean, can be detected. That means your uptake is less than production. That's why you measure the residual. And we can measure acetate, propionate, and other VFAs over time. So why VFA composition and production rate matter? First, we know that the PAOs and the GAOs have quite a different kinetic rates towards different VFA and the preference towards different VFA. And we have a previous evidence showing that higher propionate to acetate ratio actually favors PAOs over GAOs. That's just one example. And second, we also have previous understanding that VFA feeding rates and the feeding mode, like a continuous feeding, low concentration, or batch feeding, etc., can actually affect the population selection. And due to the fact that by different feeding modes, you're giving advantage to PAOs, GAOs that may have varying K sub S half saturation rate as well as a maximum substrate uptake rate. So depending your KS strategies or KMAS structures, depending on your feeding mode and concentration, you will have different population selection. And at very last, more complex the VFA composition is expected to enrich for more diverse PAOs. And more diverse PAOs in ecology sense translate or implies that you may have more robust or more resistant population function, therefore translate into more robust EBPR activity. So that's the mechanism 1. So we learned that the VFA production rate and quantitatively and what's the composition. So the mechanism 2 is probably the core one. is why Sidestream EBPR conditions would favor PAOs over GAOs. So specific question we had in mind is that first, what really happens to PAOs in the Sidestream when exposed to deep anaerobic condition for extended long period of time, up to 72 hours or 2 and 3 days, which is much, much longer than anaerobic condition in conventional anaerobic zone design. And so what is the fate of PAO? Do they die? Do they stay there? And what is the phenotype and the genotype and potential changes during that period of time? And we also, of course, want to know what happens to GAOs at the same time, as well as what are the fate of other organisms, because they are also dominating ones in the whole population. So what we learned that in the Sidestream reactor under deep anaerobic condition with extended period, PAOs actually stay alive for up to at least 48 to 72 hours through our testing, and there's other literature indicating it can be even longer. And not only they stay alive during that time, actually PAOs actively uptaking VFAs and produce PHAs. We have evidence of both bulk chemical measurement as well as individual cellular inside the cell PAO production rate by Raman, both to show that indeed PHA production is proportionally accompanied simultaneously with the VFA uptaken. And we also taking sludge samples during this testing period, periodically taken out to do on-the-side uptake release testing at a different time period to evaluate the EBPR activity and stoichiometries, and also clearly, repeatedly showing that the EBPR activity actually I call it potential activity, increased over, during this anaerobic incubation time. So this is just one example to support the statement I made above. So this is one result to show that we use the fish fluorescence in situ hybridization. Note that fish using probe measure messenger RNA, so they actually supposed to measure the live active cells before they're fixed. So as you can see that the samples taken out at a different period of time and different time points during the anaerobic starvation time, the population of the measurable and the known PAO-GAOs, for which fish probes are available, showing that the population stayed statistically rather constant, sometimes even slightly increased, but overall statistically considered a variation of the error, they stay rather constant. This is another example slide to demonstrate the point that during the anaerobic Sidestream batch testing, you can see the phosphorus release, the VFA production simultaneously, as well as intracellular PHA production, as I mentioned earlier. And then up to a certain point, they start to plateau out. And this transit point seems to vary from plant to plant. And this is the result to show that when we taking the samples out at a different time period, then do a uptake release testing on the site to measure the EBPR activity. For this figure particularly, we show the normalized aerobic P uptake rate comparison as indicator of EBPR activity. As you can see that for both South Carey and Rock Creek, the rates actually increased over the anaerobic incubation time. Once again, I want to point out the transit time. So for South Carey, up to 36 hours or even 40, the rate continued to increase all the way until 72 hours. And for Rock Creek, the transit hour is much earlier at 18 hours. This transit hour is critical because for optimization, we really want to design conditions such that actually the EBPR activity is relatively at its highest in the peak time. So that's another factor need to be considered for future design guidance. And then, of course, we try to understand that the known population changes through that period as well. So this particular result shows the PAO and the GAO abundance, only the known ones. In here, we showed Acuminobacter as well as tetraspheral, as well as the known candidate GAO abundance in this 4 Sidestream EBPR plants participated in the survey. So the key findings, we found that actually, even though the performance I showed earlier through the statistical survey proves different. So the known population for Acuminobacter and Tetrasphaera, they both found relatively abundant in the Sidestream EB plants. However, their abundance level compared to the conventional, we do not see much statistical actually shift or differences. They're relatively comparable. And there is consistent observation of low known GAO abundance, with exception of an Henderson plant. But what is consistent, is that when you look at not just the known PLGO such as Cumulaca tetrasphaera, if you look at the entire microbial population of the whole sludge, to look at the microbial diversity measured here as a Shannon or inverse Simpson index, the difference is statistically clear that the Sidestream definitely provided a higher microbial diversity index. I think this is really more important. It's that even though the known PLGOs, they don't show or exert much difference between the two systems in comparison, but there's a clear shift and increasement in the microbial diversity, which implies that there are unknown PLs, GAOs in the system. Our known probes cannot detect there. We still need to identify, discover, understand them better, but also disregard, even though we don't know who they are, the fact that the Sidestream configuration really enriched and increased the microbial diversity holds the key for improved performance, particularly for stability. Of course, much more detail still need to be reviewed. But however, I do want to point out that even though using just a simple amplicon sequencing level comparison or fish probe targeting only the known one, we were not able to see statistically difference between Sidestream and conventional. However, when we tried further to look into detail of so-called microdiversity within the known Acuminobacter, with the most commonly studied group of PAOs in the system, we start to see the difference. So this is a technique we explored and successfully. It's using oligotyping. It's a data processing, data computation method allow us to actually resolve one single base pair differences of the 16S sequence of Acuminobacter clade sequences. So as you can see in this particular figure, the key point I want to demonstrate here is that on the right-hand side for the Sidestream configuration, there is a clear enrichment of the orange-colored oligotype number 2. And not only it's clearly become more dominant, it actually become more and more dominant during the period of time of the pilot testing at Rock Creek. And that's where we see the performance improve and performance different at the same time. So therefore, that led us to believe that the system actually did select for population shift to a different subclade of Acuminobacter, even though overall abundance didn't seem to differ statistically. So this holds another important key for us to understand the better macro diversity level differences of the key PAOs in these two systems. So we conclude that the community fingerprints did indeed show differences in the conventional A2O and the Sidestream EBPR at the finer resolution beyond commonly used 16S OTU level. And Acuminobacter clades are indeed different between the Sidestream and conventional, and which probably more likely associated with the kinetic differences and VSA preferences, which need further investigation. And to further resolve the genomic differences, which indicating the potential phenotypes, we also go beyond just the 16S, also did a whole genome metagenomic analysis using genome resolved metagenomics of Acuminobacter in this facilities to get a better understanding. And long story short, the metagenomic analysis indeed discovered the new Acuminobacter max from the full scale for the first time, never been reported before, including one very unique Acuminobacter genome specifically associated with Sidestream EBPR, which would need further evaluation. And the next key point I want to present here, also related to mechanism 2, is the evidence of sequential polymer usage in PAOs. It has implications in decay and computation between PAOs and GAOs. This is a figure to show that during the anaerobic extended starvation time simulating the Sidestream condition, the single-cell ramen combined with genomics allow us to review the temporal trends of the polymer, including polyphosphate, glycogen, and the PHA in both individual PAO cells and the GAO cells over time, and to observe their trends. So the key point I want to point out here is that the result shows that the polyphosphate in the PAO is shown pretty quick consumption during the anaerobic starvation time, indicating that the PAO at the beginning is quickly using poly-P as the energy source for maintenance under anaerobic condition. And then as soon as the poly-P being consumed, PAO can actually transit into more dominant glycogen usage, as you can see from the second figure. As soon as the poly-P level individual cells drop to a certain level, the glycogen will start being the dominating energy source to maintain the PAO in the system. In contrast, on the most right, because GAOs does not have poly-P polymer, only have glycogen, so they actually quickly consume the glycogen at the very beginning of the anaerobic stage. As soon as the glycogen drops below a certain threshold level, GAOs have to start to decay because they only have one polymer. So this actually have great implication, meaning that due to the dual polymer position and the very flexible, we call it elasticity of the pathway PAOs possess due to the bioavailability in the different combination of poly-P and glycogen, PAOs can use different pathways, glycolysis, TCA cycle, reverse cycle, etc., or shunt to allow PAOs to sequentially, or at least using different ratio of the poly-P glycogen to maintain much longer time before they kick into decay, rather than GAOs, which can kick into decay very quickly after glycogen being consumed. Computation among PAOs, GAOs, and other organisms. This is an oversimplified figure with the aim to illustrate the overall trend and fate of the three major organisms, to illustrate the computation among them. So based on the mechanisms and activities as I described earlier in earlier slides, PAO, due to the versatile biochemical pathway and capability and the different intracellular polymer to provide the energy and the maintenance energy, PAO can sustain and stay live within extended anaerobic conditions for quite a long time. They were also able to uptake VFA and store PHA, and eventually, when all the intracellular polymer depleted below the threshold level, they will start to decay. And in parallel, GAO will also be able to stay live at the beginning when intracellular polymer is available as energy source, and then after that's depleted, they will start to decay. But the onset of the decay of GAO is expected, and based on the evidence results we show from our study as well as in the literature, the onset is earlier and sometimes much earlier than the PAOs. And at the end, all the other heterotrophic organisms are expected to decay rather early on, and as soon as the anaerobic condition hits, and they will be the major sources to provide the fermentation carbon sources. So again, in a very simplified vision of this, the key message is that under extended anaerobic conditions, there is apparent overall system level carbon, I call it reshift, meaning that the fermentation would release the carbon from mostly OHOs, and the carbon can be uptaken again by the PHA, therefore cause the overall carbon reshift. There another element essential I want to illustrate on this figure is the time during the anaerobic incubation time. As you can see on the figure that at the beginning of the stage, both PAO and GAO can stay alive. And in somewhere in between the time, there will be in the middle, as I draw between the two vertical lines, the differential decay rate between the PAO and the GAO is actually a key factor that gave the PAO competitive leverage, a competitive favor over GAOs. But I want to correct for one typical misunderstanding. When you have conditions favor PAO over GAO, it does not mean that you're going to eliminate the GAO or your system don't have a GAO. That's completely not supported by observation evidence as well as theory. Actually, if your carbon is provided in excessive amounts over the stoichiometry needed for the maximum amount of PAO can grow in your system, the actual surplus carbon has to go somewhere. Typically, in this kind of condition, with this anaerobic or feast famine condition, they will go to GAOs, as well as other organisms are able to pick up a carbon. For example, PHA accumulating organisms. We have found that in typical Sidestream EBPR systems, there are statistically significant increase of a PHA accumulating organisms, which has been recently proved again in other systems we studied. So to summarize again, to clarify some of the key information or message we learned so far regarding the computation among organisms. Number one, people ask, so is Sidestream EBPR select different PAO? And the answer is that so far, based on the evidence we have, there seems to be increased the total diversity as well as abundance and the corresponding EBPR activity in Sidestream compared to conventional. And more importantly, through oligotyping and higher resolution molecular tools, beyond just amplicon sequencing, we were able to show that actually the subclades or so-called microdiversity of even just Acuminobacter are different in the Sidestream compared to the conventional. So therefore, their likelihood there are in reach for different subclades of Acuminobacter, as well as other unknown PAOs in the system, which would still need further investigation. The second question relates to Tetrasphaera. There were intuitive hypotheses or assumptions that the Tetrasphaera may be more properly enriched in Sidestream system due to their capability to use a higher diversity of substrates as well as a capability to ferment. However, based on both surveys in Denmark by Per Nelson's group, as well as our study in North America of the treatment plants in this region, so far there's no statistical support evidence to show there's definitely higher abundance of Tetrasphaera in Sidestream compared to conventional. So therefore, that's also need further investigation. But we do see abundance of Tetrasphaera in both Sidestream as well as conventional systems. The third question related to GAOs. Previous study from Denmark side indicated that Sidestream seemed to have a consistently lower known GAOs compared to conventional. Our observation is consistent with that, but remember the keyword is known. If you only look at the currently known candidate GAOs, there seem to be consistent lower in Sidestream. However, using Raman, which can capture the total GAO, including both known and unknown, we found that not actually true. So, like I said earlier, if you have excessive amount of carbon, you are bound to have GAOs. You cannot avoid it. And they will be theoretically and supported by evidence that we will have GAO inside the stream, and they may have different types of GAOs rather than the known typical ones we observe in conventional systems. And at the very last, we have consistently observed a significant increase of the abundance of a PHA accumulating organs in the Sidestream systems, which I will show further evidence later, and their physiology, their potential contribution to either phosphorus removal or denitrification are still under investigation. The third mechanism I want to highlight a couple of key findings are related to the phenotypic or so-called functional metabolic trait shift in PAOs in Sidestream compared to conventional. One of the key ones, as I mentioned earlier, is the PHA accumulating amount increase in PAOs, as well as PHA-containing organisms overall increase. The figure here to show the comparison of Sidestream and conventional, it doesn't matter we feed acetate as the substrate or using primary fermentation supernatant to more realistically stimulating the carbon sources. In either case, you can see a clearly statistically increase of the PHA content in PO as well as the increase of PHA accumulating organisms. So this implication related to this is that when PAOs having much higher PHA during the anaerobic phase before the heat aerobic phase will give them more power, so-called burning or energy power, to enable them to have more phosphorus uptake capacity, which are associated with improved or better performance. Again, what are the other roles this PHA accumulating organism can play in the system are still under investigation. Another angle related to metabolic phenotypic shift are related to biochemical pathways. This is rather complex. There's a lot of information and the debate and discussion behind this. Due to time, I won't be able to go to very much in depth, but there are a couple key messages I want to share. One is that Sidestream EBPR processes may aid in facilitating the activity of the glycolysis pathway with increased parameter stoichiometry supporting that. This is consistent with the previous study as well. But this could result in, from either or both, increase of application or utilization of glycolysis pathway in PAOs, as also possibilities just due to the increase or higher abundance of other unknown GLOs in the system, which would need to be further investigated at a finer resolution. Secondly, in contrast, in South Carey, which is the only long-term running two Sidestream EBPR as SR configuration in the United States, we found that it has actually much lower glycogen to HAC ratio, indicating actually extensive or more utilization of TCA cycle. We did a further modeling simulation with both batch dense and full-scale data, which confirmed that. So again, the pathway diversity and flexibility is still a topic of we need to further gain better understanding. And the very last, I want to point out that both influence the carbon to P ratio, carbon level, carbon composition, VFA composition, as well as the availability and stoichiometry of different intracellular polymers, all in together affect metabolic and biochemical pathway shifts. And to address all these insights or understanding we gained so far, I want to just show one slide to point to the necessity for us to further improve our mechanistic framework and computation related to the Sidestream EBPR model, which potentially can explain why current model often fails to capture the observation we see at the full scale or batch testing. So it's rather also another complete separate topic on modeling, but today I want to point out two important factors. So the model based on original ASM2 model compared to the agent-based model we have exercised in this particular project, the key changes I want to touch upon. One is that we included the PAO and the GAO in the system, but more importantly, we incorporated the switch function allow the PAO and GAO to use different proportion of the glycolysis, TCA cycles, as well as the poly P utilization as a way to provide the ATP and NADH balance. And we allow the system to have a flexibility and the versatility to use these three different pathways depending on the ratio and availability of the different intracellular polymers. And the last point is that we also incorporate the mechanism framework to consider staged maintenance and the decay for GAOs and PAOs depending on their sequential and preferred use of a polymer as well as the utilization. So those key changes, I think, contributed to the improved performance and our ability to capture and predict the Sidestream EBPR system. And at my last slide, I want to show some key points how I see that this fundamental and mechanistic level understanding and insight we have so far can help or be associated with further design of Sidestream systems. So I will only touch upon 3 key things, and I think James will also further provide his experience and observation in the next section of the slide. So first parameter I want to touch upon is SRT. We do need to provide sufficient SRT to allow hydrolysis and fermentation occurring in the Sidestream reactor to provide the DSA. However, we also at the same time do not want to overdo and to encourage methanogenesis, which would just guide you or shift your carbon to different channels. And also, we can supplement carbon to the Sidestream if the SRT is shorter or do not have enough volume. However, that can be overcome potentially by intermittent mixing, we'll discuss later. And also, I think we need to do further and better understanding of the issues or potential benefits associated with the excessive or just enough carbon provided by the Sidestream, either through internal fermentation or additional supplements. We have evidence to show that excessive carbon actually would potentially lead to other issues, which I will not discuss here, such as encourage excessive amount of PHA accumulating organisms in the mainstream treatment, which we have other implications and consequences, but is beyond the discussion of today. Second is related to HRT. HRT is also another important factor for the reasons I described earlier, especially that figure I showed earlier to show that there is a optimized time range that the PAOs can maximize the PHA accumulation inside the cell. Excessively long HRT actually would lead to decay for all organisms, but too short, you are not fully utilizing ROPF to maximize the PHA within the PAO cells. And also it's critical due to the fact that you want to stay in the zone such that the competition favor for PAOs over GAO is being optimized. And the last, how do we optimize the system? Still need a more accessible, practical, cost-effective tools as well as computation capability. And the very last, the mixing. Intermittent mixing would potentially allow us to decouple the SRT and HRT in the Sidestream system to provide the fermentation, even your Sidestream reactor is not larger enough to enable longer SRT. By doing intermittent mixing, you would allow that. And there will be other settling or the other issues, and I think James would provide more insight. So from next slide on, I'll give back to Dr. James Barnard. Thank you.
Well, we'll give you some examples of where we have applied this technology. And the first one here shows Anderson, which is one of the plants that was studied by Professor Gu. And this plant was designed in an area where there was a lot of volatile fatty acids in the influent. There were no primary tanks. This was an upgrade of a carousel system by putting more aeration in and adding anoxic and anaerobic zones up front. The plant performed well until one day when it stopped removing phosphorus, and it was discovered that nitrates were added to the collection system for odor control, which destroyed the VFA in the influent. And what then happened is we switched off mixer. There were 3 anaerobic zones, and we switched off a mixer in the central one, and that allowed the sludge to settle. That was one of the examples that was shown, and ferment. And there was an exchange of mixed liquor between the bottom portion, the anaerobic layer, and the mixed liquor on top. And the line that you see here, and around about 0.1, that was the orthophosphate out of the final clarifiers. They needed to get down to very low values, so what you see lower down is the effluent phosphorus after some tertiary chemical treatment. Here's another example of the Stickney plant in Chicago. It's an 800 MGD plant, and it's a 4-pass aerobic system, or multiple units of 4-pass. And what has happened is air was switched off in the first half of the 4 passes. and that resulted in the phosphorus being removed. The phosphorus being removed then, in this case, in this very large plant, went, of course, to the digesters, and it was returned to, or some of it was returned to the plant. But in the meantime, a Ostara struvite system was installed here on the Sidestream to intercept that phosphorus and to produce struvite. On the next, that was the site of the Ostara plant. On the next plant, we showed what happened at the Cedar Creek plant, where we actually used the Sidestream fermentation, where we took some mixed liquor from the anaerobic zone. We kept it under anaerobic conditions for about 1.5 days, SRT, and that was actually returned to initially to the anaerobic zone, but eventually to the anoxic zone, because they were more interested in getting the nitrogen down, with the idea that they could always add chemicals, but the plant has performed very well without having to add chemicals in terms of both nitrogen and phosphorus removal. The other slide and the other diagram on the right-hand side, that is the Sacramento plant is a 180 MGD plant, and that was upgraded for, or is being upgraded, in fact, it's under construction right now, for nitrogen removal. But in the end, they decided they also needed to get the phosphorus removal. And we did exactly the similar thing as the sketch shows on the left in the pilot plant by putting in Sidestream fermentation in from the anaerobic zone. And what you see on the left-hand side here is the initial phosphorus coming out of the process. And there was acetate added to bring it down to very low values. The acetate was stopped at the point here on the red line, and it was allowed to get back up to normal again. Some of the flow was bypassed around the anaerobic zone, and at that time the fermenter was switched on, and you can see how the phosphate dropped down to quite low levels, and here it was switched back on again. This is what happened in Denmark, where they had an anaerobic aerobic system, and they fermented a portion of the return sludge, 10 to 30%, in an anaerobic tank, and created those anaerobic conditions. So you can see here there was no formal anaerobic zone, and about, well, say 80 to 90% of the RAS was just simply bypassed into the anoxic zone. That's been extremely successful. What they have discovered, as Professor Gu has explained, is that they could reduce the influence of the GAOs in this process, so they refer to it as GA busters. On the next slide, we see what happened in South Carey, where they did the Sidestream fermentation. You can see it's a 4-stage nitrification, denitrification process. On the Sidestream, all of the RAS goes through an anoxic stage and then an anaerobic stage, and some of that is fermented. It's about 7% of that flow and brought back to the anaerobic zone. But notice that the influent goes into the aeration zone. The next slide shows an example of what happened at Denver Metro. Denver Metro, it was one portion of the plant was a 100 MGD plant, and they had these RAS nitrification basins called carb basins, and we used 2 of them as Sidestream fermenters. So about 18% of the RAS and the gravity thickener overflow was going in here. And on the next slide, you actually see that more clearly. And this is the encircled in red is the portion that was partitioned for the anaerobic Sidestream fermenter. And here you see the gravity thickeners below, and the gravity thickener overflow was piped in there. And that has been extremely successful, bringing the orthophosphorus down to about 0.1 milligram per liter. And the slide that I'm showing here is more recent plant. It's been operated for a year now, and there are some things that one can demonstrate here. In the first place, there is a question about the value of the oxidation reduction potential. And what we did here is we had two of them. One was fixed, and that read consistently lower than the handheld one. But the handheld ORP meter was put in for about 2 hours, and then the reading was taken here. And what was interesting here is now you can look at the scale. This is the startup of the plant, where we had a Sidestream fermenter, again similar to the one I've described before for Cedar Creek, where sludge was taken out of the anaerobic zone and fermented and put back in. And you can see here how the phosphorus went down to quite low levels. Then we had a problem that the fermenter was actually too large, and what Professor Gu explained about is that you can go into methogenesis, and this happened at this point, and we started losing nitrification. So we emptied out the basin, and that happened twice until a more steady state was found. But at this steady state position here, we found that we had orthophosphorus way down below 0.1 milligram per liter. And what is interesting here is you can see that the ORP also was lower at this point when we were down there, and you can see almost a correlation between the ORP and the phosphate in the effluent. The next slide shows a number of examples. There are probably about 75 plants now operating in this Sidestream mode, and it can be applied in various ways. If you look at the pilot plant, for instance, you see if the Sidestream is on the second anoxic zone, sometimes it's on the first anoxic zone. So there are many ways in which you can do that, and that the promise of that is great in that we can really, almost any activated sludge plant can be converted to a phosphate removal plant using Sidestream fermentation. At the present, well, yes, how do we design it? Some experience. At present, there's no verified models are available for design. We must design on experience. Our experience showed to date that if we divert about 10% of the RAS to the Sidestream fermenter, and it is especially useful where you do have, where you don't concentrate on also nitrogen reduction. And we have one plant where the effluent nitrate is running at about 20 milligram per liter. That doesn't affect the process because we only divert 10%, so that's only 10% of the nitrate load going into the fermenter. And in a plug flow fermenter, that is soon it disappears. If you have a Sidestream fermenter, RAS or mixed liquor, we find that we need, I would adjust this 12 to 48 hours, but HRT, sorry, can be 12 to 48 hours, but the SRT down below here, as you can see, needs to be about 1.5 to 2 days SRT in a fermenter like that. The minute you add some primary gravity thickener overflow, that can be reduced to almost an 8-hour retention. So the fermenter effluent can go directly to the anaerobic zone. The size of the fermenter could be reduced by switching off mixers for most of the time, which will allow the thickening of the sludge to go to 1%. Professor Gu mentioned that we can separate the SRT from the HRT by controlling the mixers, and that is what we mostly do in this type of plant. So when adding gravity thickener overflow, then the SRT could be reduced to only 12 hours. For continuous mixing, the mixing energy is very, very important, because what we have found is with too high mixing energy, we actually introduce oxygen at the front end that prevents the deeper anaerobic conditions from happening. So for continuous mixing, and this is what we use at Denver, we use 0.08 horsepower per 1,000 cubic foot. And this is almost a tenth of what you will see in some manuals where they still say that you should be using like 0.75 horsepower per 1,000 cubic foot. That is, it's detrimental to the process. For intermittent mixing, we suggest with top entry mixers, more efficient mixing of about 0.12, and that can be mixed twice per day for about 30 minutes. One can determine the SRT by calculating the mass during mixing and then calculate what is wasted and what that SRT comes to. So going on with future work, I think at this point I'm going to hand back to Professor Gu.
So at the end, I would like to give a brief introduction of some of the ongoing work and the future work related to this particular project. So at this moment, Black Leach, Leon Downing, James, myself, and many others on the team are working on a different work project, which is to develop more detailed design manual and guidance, as well as assessment and monitoring toolbox to help further and wider implementation of this Sidestream technology. And secondly, I think as a separate, there are also initiatives for people working together trying to develop practical optimization and diagnostic tool sets, trying to developing a formal document, for example, of detailed protocol, how to do uptake release testing, how to evaluate EBPR activity, etc. And part of this effort will be part of the work project I mentioned earlier, led by BV. And the third one, I think there are also initiatives, people who trying to work specifically on establish models or revise and modify and improve current models for full-scale food plant simulation and modeling. And at the very last, I think related to some of the previous questions or unknowns, I mentioned that there are still many opening and unknown questions. For example, is this configuration comparable with other carbon energy recovery or conservative technology such as AB stage or shortcut NMOX and removal processes, nitrate shunt processes? Can they be compatible, make all of them working together in one system? So we have another work-funded project right now ongoing, investigate this particular subject. And at the very last, I want to see my gratefulness and thank you again to Dr. James Barnett for his vision, his guidance, and sharing his experiences with us, as well as all the team members on the WRF project. Many facilities, I think I would like to thank the funding provided by WRF, HRSD, Woodard Current, as well as all the participating facilities, including City of Olays, Greater Chicago, Denver Metro, Henderson, Western Side Regional, City of Meridian, City of Cary, Upper Blackstone, Town of North Attleboro, City of Westfield, the Town of Erie, City of Kalispell. I'm sorry if I missed anybody, but really grateful for all the team and contributing members on the Sidestream EBPR project. Thank you again. I give it back to
Thank you both. Thank you very much. Thank you both for a great presentation today. That concludes our webcast for today. Be sure to look for it on demand, and want to wish you all a very nice afternoon. Have a great day. Thank you.
Thank you. Bye.